Okay, guys, welcome again. Last time we have studied the balancing the chemical equation, right? And we learned how to balance chemical equation, how do we do the stoichiometric calculation. Lots of things you have studied last time. So okay, this time we will learn about the limiting reactions. Okay, so metathesis reactions, right? Precipitation reactions, and the net ionic equation, complete ionic equation, molecular equations. These very important things we are gonna study today. Okay, now let's ready to study that. So let's start from the limiting reactants. Okay, if you think last time we have studied about the different chemical reactions, and but you know that if you mix, for example, you are doing the experiment in the lab. So suppose that you have reactant A and reactant B. So if you mix some proportion, equal proportion, equivalent molar proportion, then everything gonna react. But if you don't do that, if you have not equal molar proportions of two reactants, then one reactant will left behind, right? One reactant will left unreacted. It will be, and other reactant will completely finished off, right? So whatever the completely finished off, that is said to be the limiting reactant. And whatever is not finished off, still left behind unreacted, that is said to be the excess reactant. So now let's see some analogs here for that. You see, you are making some ice cream. Okay, it means they're doing reaction. So the formula is you add 2 scoops of the ice cream and add 1 cherry and 100 ml of the 50 ml of syrup. You give the 1 sundae. Okay, so and similarly you have 4 scoop, you need what, 2 cherry, and you need what, 100 ml, then you give up 2 scoop. But whatever you have mixed, you have available how many scoops? 1 2 3 4 5 6 7 8 scoops. And how many cherries? 1 2 3 4 cherries. Then look at that, 2 scoop equal to 1 cherry, other 2 scoop equal to 1 cherry, but still you have 2 cherry left behind, right? That's it. Pretty simple, right? The whatever the left behind is the excess. These 4 scoops and these guys are left behind because you have only 100 ml syrup. If 100 ml syrup means 50 ml syrup means 1 sundae. 100 ml syrup means 2 sundae. To make the 2 sundae, you need the 2 cherry. You need the 2 cherry. To make the 2 sundae, you need the 4 scoops. You need the 4 scoops, but still you have 4 scoops left behind, 4 cherry left behind, right? So you are making, you have available how many scoops? 1 2 3 4 5 6 7 8 scoops of ice cream, and you have available 1 2 3 4 5 6 cherries. These are cherries. Okay, you have 6 cherries and 8 scoops, and you have 100 ml syrup, 100 ml. This, and but you cannot mix all of them, right? Because you have syrup only 100 ml. Because the 50 ml syrup means that 50 ml means 1 sundae, and the other 50 ml means second sundae. That's why you only can make 2 sundae. However, you have a more than enough ice cream, more than enough cherries, but you can only make the 2 sundae, right? So that's why how many to make the 2 sundae, you need the 2 sundae, right? How many cherries you need? 2 cherries you need, right? 2 cherries you need. How many scoops you need? 4 scoops you need. So 4 scoops, 2 cherry, 50 ml. Look at that, these are left behind. These are left out. So that's why whatever completely goes away, syrup, that is the limiting. We have limiting amount of that, and we have more than enough amount of that. So that's why these are excess. These cherries are also excess, but we have limited amount of the syrup. Okay, that's the concept, that's the analog. Same thing happens in the chemical reactions also. Okay, guys. So that now let's take some other examples. Okay, nitrogen plus oxygen gives you 2 NO2. Okay, before reaction, let's say 5 gram of nitrogen. Okay, so 5 mole of nitrogen and you have 1 mole of oxygen. So what is this reaction tells you? This reaction tells you 1 mole of nitrogen react is equivalent with 1 mole of oxygen, right guys? So you need how many moles of oxygen? 2 NO2 means 2 times 2, 4O, right? Okay, it's O2 means 2 O2. Let me erase everything and go again. Okay, so let's see that here. So N2 plus O2 gives you 2NO gas. Now this is your balance equation, right? How many oxygen? 2 oxygen, 2 oxygen. How many? This is balance equation. Now what did this equation say? That 1 mole of N2 equals to 1 mole of O2. This tells us that, right? But suppose that if you use 5 mole of N2, what happens? What happens? If you use 5 mole of N2, then following thing is happening, guys. Now, so this means N2 plus O2 gives you 2NO. This means that 1 mole react with 1 mole gives you 2 mole, right? And but you have 5 mole of nitrogen and 1 mole of oxygen. Suppose that if you have 5 mole of nitrogen and 1 mole of oxygen, what happens? What happens then is following thing it happens. Okay, so 5 mole of, if you have 5 mole of nitrogen in nitrogen cylinder and 1 mole of oxygen, what happens is 1 mole of oxygen means 1 mole of nitrogen, right? So 1 mole of O2 will consume 1 mole of N2. So only 1 mole of N2 will be used here. All other moles will be left behind there, right? So 5 minus 1 equals to 4 mole of N2 will remain unreacted. So that's more than enough. You need only 1 mole to react with 1 mole oxygen, 1 mole of nitrogen to you need only 1 mole of nitrogen to react with 1 mole of oxygen. But you have 5 mole of nitrogen but only 1 mole of oxygen. It means that 1 will consume 1 but left is 4, right? So remaining will be left. So N2, so O2, 2NO. What is happening? Initial you have N2 means you have a 5 mole. Initially you have oxygen is what? 1 mole. Initially NO is not remain. Initially this is the product, right? Initially you don't have product, right? After reaction you will have product. So initially you don't have product. So but after reaction 1 mole of oxygen will consume 1 mole of nitrogen. That's why minus. So change, and this is also 1. This is also 1. This is also forms 2 mole, right? 2 times 1. So that's why what is the final? How many moles of nitrogen will be left behind? 4. How many moles of oxygen will be left behind? 0. Nothing. How many mole of the nitrogen oxide, nitrous oxide will form? 2 mole. That's why this 4 is said to be the excess reagent. This 4 is said to be the excess. Okay, this is said to be the excess. This is 0. This all everything finished away. Everything finished. That's why this is said to be the limiting. This is said to be the limiting, and this is said to be the excess. Okay, whatever is completely consumed, that is limiting, and whatever is left behind, that is said to be the excess. How do we know that? by the mole relationship between reactant and the product. Okay, so that is the limiting reactant. So let's see some example. Let's see some example to understand. So let's see that here. This is, you have one some container you have, and it has 3 chlorine. Look at that, 3 chlorine. It has 3 chlorine. Chlorines are in green. 3 chlorines. 3 chlorines. 1 Cl2. 1 chlorine. Other chlorine. Other chlorine. This is Cl2. That's why 1 sphere for one sphere for 1 chlorine, other sphere for other chlorine, other for other. This is Cl2. Okay, and there are 6, that is in the yellow color. There are 6 fluorines. Look at that, fluorine are yellow. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 fluorine. This is the scenario. Okay, so what is the reaction? Reaction is this: Cl2 gas, fluorine also highly reactive gas. Okay, 3F2 gas gives you 2ClF3 gas. This is your reaction. Okay, so what is present here? What is present here? You have chlorine is equals to Cl2 is equals to 3 mole, 3 molecules, 1, 2, 3, and fluorine is equal to 6. 1, 2, 3, 4, 5, 6. Right? You can count here. 1, 2, 3, 1, 2, 3, 4, 5, 6. So that's why fluorine F2 is equals to 6 mole. So this is your scenario in your reaction beaker. So what your equation say, that 1 mole of chlorine is equivalent to 3 mole of fluorine. So see that how many mole of the chlorine you have? 3 mole of chlorine, right? 3 mole of chlorine is equivalent to what? 3 times 3 mole of fluorine, right? But we don't have 3 times 3 mole, right? We have only 6 mole of the fluorine. So you know what will be finished then? What will be finished then? So what is the finish? So you need this 9 mole of F2, right? But you don't have 9 mole of F2. You have only 6 mole of F2. So fluorine will finish fast, right? Chlorine will be still there, because chlorine needs all. If you want to react all of these chlorines, you need the 9 fluorine, but you don't have 9 fluorine. Means fluorine will be completely used up. Chlorine will be still left behind, right? So that's why fluorine is limiting. But this is the way. But how do we calculate that, right? Let's calculate a little bit. We need a better idea. So better idea is, that is the limiting. That is the limiting. Limiting is that which produce less product. If you completely used all of these reagent and the produced the less amount of the product, then that is your limiting. Okay, so what does it mean? So you have a fluorine is equals to 6 mole, chlorine is equals to 3 mole, and if you use all of these, and if you use all of these, then how much product can form? If you use all of fluorine, how much product form? If you use all of chlorine, how much product will form? Calculate that. And which will product less amount of the product, which will reproduce the less amount of the product, that is the limiting. Okay, so for example, fluorine is 6 mole, right? So look at that here. 3 mole of fluorine produce 2 mole of the product, right? 3 F2 is equivalent to 2 ClF3, right? This 2 ClF3. So but you have how many moles? 6F2 is equivalent to 2 by 3. See, 2 by 3 times 6F2 is equals to 4 mole of ClF3. Okay, so fluorine, all of fluorine produce 4 mole of ClF3. Now let's find out all of chlorine how much produce. Okay, so let's go to the chlorine relationship. Now let me take the another color for the chlorine relationship, and it will be easy to distinguish, right? Okay, now then the chlorine and the product relation says that 1 chlorine is equivalent to 2 ClF3. Okay, so 1 chlorine is equal to that, but you have how many chlorines? 3. 3 chlorine is equivalent to 3 times 2 ClF3 equal to 6 ClF3. So that's why, let me rewrite that again. Let's see that 6 fluorine produce 4 mole of product. 3 chlorine will give you 6 mole of product. If all of chlorine is used, you will produce 6. Which produce less? That's why fluorine produce less product. So F2 is limiting. So this is the way of finding which is limiting. If fluorine is limiting, automatically chlorine will be excess. Okay, let's go further. Now, so that's fine. Now let's make a table, ice table. Okay, so we have a Cl2 gas plus 3F2 gas give you 2 ClF3 gas. Okay, so this is initially how many chlorines? 3 chlorines. How many fluorines? 6 fluorines. How many products? No product. Initially 0 product. After reaction, what will be changed? So look at that. All fluorine will be used? Yes, because they are excess, right? All fluorine will be used. They are 6. But 6 fluorine equal to how many chlorines? Look at that. So 1 Cl2 is equals to 3F2, right? You have 3 Cl2. See, all of 3 are not using. That's why 3F2 is equals to 1 chlorine, and 6F2 is equals to 1 by 3 times 6 chlorine is equals to 2 chlorine, right? That's why 2 chlorine will be changed here, and that will be how many? 1 chlorine equal to 2 product, right? Means that way you have used 1, that's why 2. 2 times 2 is 2 times 2 is equals to 4. So, and that's why final, what will be final? 3 minus 2 is equals to 1. This is 0, this is 4. That's why what is the limiting? Limiting will be fluorine, and the excess will be chlorine. And how much left unreacted? Left unreacted is equals to 1. What is the left behind is 1. So 1 mole will be left behind. So this is the concept of the limiting reactant, limiting and the excess reactant. So now let's see here one example, one good example here, that is calculating limiting reactant. Okay, now let us calculate the limiting reactant. So okay, now let's do some calculating a limiting reactant. There's some problem, and then it will help to understand better. Okay, in another preparation of ClF3, 0.75 mole of chlorine react with 3 mole of fluorine. Find the limiting reactant. Write the reaction table for that. Okay, so now let's see the reaction. What is the reaction? Reaction is, I see reaction is here. Chlorine plus 3 fluorine gives you this. Okay, so let's find out that how much chlorine. So chlorine plus 3 fluorine, it's a gas. Okay guys, and chlorine is also gas, gives you 2 ClF3. This is also gas. So how many moles of the chlorine? 0.75. So this relation tells us that 1 mole of chlorine equivalent to 2 mole of ClF3. So but you have 0.75. Okay, 0.75 mole of Cl2 equivalent to 2 times 0.75, that is equals to 1.5 mole of product, right? So ClF3. This is that gives, chlorine gives that. Now on the other hand, now this gives 1.5 mole. Okay guys, now other is 3 mole. 3 mole of 3F2 is equivalent to 2ClF3, right? But how many moles? 3 mole of, okay, so this means 2 mole, right? Oh, okay, it's easy for comparison. So one produce 1.5 mole, other produce 2 mole. Which produce more? Fluorine produce more, right? So fluorine produce more ClF3 and the chlorine produce less. That's why limiting reactant is equals to chlorine. And how much product that will give? That will give 1.5 mole product. So the theoretical yield, remember that we will use this theoretical yield term. Okay, theoretical yield is equals to, okay, product produced by limiting reactant. Okay, so what is the theoretical yield of this reaction? That is 1.5 mole ClF3, and you can convert that in the gram easily, multiplying the molar mass, right? That is equals to 1.5 times 1.5 mole times, now if you convert it into the gram, okay, ClF3 mass. Now let me calculate mass of ClF3, asking to the AI. Okay, see, very nice AI, right? Artificial intelligence, right? See, now 92.45. Okay, that is 92.45 gram per mole. So then that is calculation is 92.45 is about 140, I think. So okay, no, not that. Okay, now let me go to here. So 92.45 into 1.5, right? 92.45 times to 1.5. So that is equals to about 138.67 gram. So theoretical yield will be 168.35 gram. So done. So you see, what is the limiting reagent is chlorine. Previously, you remember that in previous case fluorine was the limiting, but in this case chlorine, same equation, because it depends upon how much amount you are using, how much amount you are using, right? What reactant and how much amount, it depends. So let's make the reaction table for that. Reaction table contains, let's see, Cl2, right? Cl2 is the gas plus 3F2, this is also gas, gives you 2ClF3, that's the gas. See, this is your equation. And now let's the reaction table. Initially, how much is the chlorine? 0.75. How much is the fluorine? You have 3. And how much is this product? 0. Now look at, chlorine is limiting, right? You see, we just find out chlorine is limiting. It means that all of the chlorine will be gone away. All of the chlorine, right? Chlorine is limiting. That's why everything gone away. So what is the change? Change is equals to minus 0.75. That is change. How much fluorine gets in? It's the same thing, right? 1 mole of the chlorine is equivalent to 3 mole of the fluorine, right? Let me calculate. 1 mole of chlorine equivalent to 3 mole fluorine. So that's why 0.75 mole. So chlorine is equals to 3 times 0.75. That is equals to okay, 2.25, right? So look at that much mole of fluorine gone away. Not all of 3, it remains excess, right? All chlorine go because it is a limiting, but this only goes how much? 2.25. that much mole. These all are the mole. Okay guys, this is a gas, this is not gram, this is the gas. And how much this will forms? 2 times, see, 2 times, okay, so 2 times 0.75, right? And that is equals to 1.5 mole. That much mole will be changed. Now what will be final? You will subtract or add, right? This subtract this gone away, and that is 0. This is 3 point minus 0.75, okay, and that is plus 1.5. So look at that. What is the limiting? Limiting is, we already found, this guy is the limiting, this is limiting. So this is excess and left unreacted, and this is your product. This is said to be theoretical yield. Okay, so this is your limiting reactant calculation. Okay, I think this is enough for calculation of the limiting reactant stoichiometry. Okay, so this is another example, similar example. You can do that, you can practice that. Everything calculation I have done here. A fuel mixture used early days of rocket consists of the 2 liquids, the hydrazine and the dinitrogen trioxide, so which ignite on the contact to form nitrogen gas and water vapor. How many grams of the nitrogen gas form when 100 grams of this are mixed? So we have already calculated this type of the calculations in this stoichiometry. And the reaction table, we just see the reaction table like that. What is the reactant, what is the excess, everything you can find out by the mole relationship. You look that. Okay, so this is the my reaction table. You can see that here. So now percentage yield, right? We see that we discussed last slide. Percentage, first of all, percentage yield. You know, if we do some reactions or in an experiment, or the experiment in the laboratory, you cannot have 100% product, right guys? You cannot yield 100%. Nobody can yield 100%. Some mistakes are there, some experimental errors are there. You have studied the experimental error, precision, accuracy, etc. in the lab section, right? When you study the lab, did you remember that? When you study the lab, we discuss about the precision, accuracy. There are errors, instrumental errors, lots of things. That's why it's very, very, very hard to get the 100% yield. So if you get 90% yield or 95% yield, that's great. So how do you do the percentage yield? Percentage yield you find. So that is actual yield divided by theoretical yield. You know, theoretical yield we have discussed in last slide. What is the theoretical yield? That yield given by that product, or yield given by the limiting reactant. How much the product produced by limiting reactant, that is your theoretical yield. Okay, and actual yield means how much you measure in your laboratory, how much you get that in actually you get in the laboratory, that is actual yield. Okay, so that is actual yield divided by theoretical yield is 100% yield, right? That's the theoretical. So how much your experiment is deviated from the 100% accuracy, that is actually percentage yield. Okay, so for example, your theoretical yield is previous case. Your theoretical yield was previous case how much? We discussed the last time, this one 1.5, right? Theoretical yield is equals to 1.5 mole. You can convert that into the gram. Okay, 131 something, we have converted that. So that much mole your theoretical yield. So that is your theoretical yield. And but you measure in the laboratory, you synthesize that, you do this reaction in lab. Actually you did this chlorine plus fluorine experiment in your lab. You get, for example, 1.2 gram. because of your inaccuracy in your instruments, inaccuracy in impurities, lots of things. Okay, because of these lots of things, you just get 1.2, you didn't get 1.5. So what is the percentage yield? Percentage yield is equals to how much you get? 1.2 gram in your laboratory, Chem 122 room, right? So Fox building, right, 221 room, right? You did the experiment there and you get the 1.2 gram, right? But theoretically you should have what? 1.5. Theoretically you should have 1.5. So let's say this is the mole. Okay, this is also mole. So what is the percentage? Just multiply that by 100 or convert that in the gram is better. Okay, instead of the mole. However, gram cancel. Mole will be multiplied with the gram, the multiplier will be cancelled, it's the same thing. But this is 1.2 by 15 is equals to, so how much is that? So that is 3 by, so 4 by 5, right? 4 by 5 times 100 is equals to about 80%. Okay, you get 80% yield and 20% is the error. So, you know, in your experiment, you have uncertainty about the 20%, right? You didn't get 20%, you lost 20%. So your theoretical yield, your actual yield, the percentage yield is 80%. That's the percentage yield. Okay, so now we have done this percentage yield. So for example, this is the example. Okay, so percentage yield is 80%. Okay, so same thing, we did the example. So let's say another example. Silicon carbide is made by reacting sand silicon dioxide, that's the carbide. Okay, silicon and with the powdered carbon at high temperature, carbon monoxide is also formed. What is the percentage yield if 51 kg of silicon carbide is recovered from processing? Very simple. So now you first of all you know the reaction. Okay, now let's see the reaction. Let me erase that. What is the reaction? Silicon dioxide, this is a solid, silica, whatever you see on the beaches, silicon dioxide, 3 carbon, right, solid, gives you silicon carbide, solid, plus 2 carbon monoxide gas. This is your reaction. This is your reaction, guys. Okay, this is your reaction. Now, what is the mole relation? Okay, 1 mole of SiO2 produce how much silicon carbide? 1 mole of silicon carbide. Okay, so that's why see that silicon dioxide, how much silicon dioxide is used? 51 kg of silicon carbide is recovered. Okay, so reacting the silicon dioxide with the powdered carbon at a high temperature, 51 kg of silicon carbide recovered from 100 kg of sand. Sand means silicon dioxide. Okay, guys, silicon dioxide. 100 kg. First of all, convert that into mole. SiO2 equals to, you see, I convert that into mole. 10 to power 3. I can first of all convert this the kg. Convert kg into the gram. 100 times 10 to the power 3 gram of silicon dioxide, and divide that by the molecular mass, right? Divide by 60.08 gram per mole, and that is equals to 1664 mole of SiO2. This much more SiO2 you use, but you recovered okay, you recovered how much only kg? 51 kg. So let's leave that kg because you convert the mole and mole into the kg. That's why this is not mole. So let's see that 1664 mole of SiO2 should be equals to this, right? If all of them used. Okay, but here 3 carbide is used, 3 carbon is used. Okay, so that is equals to, because 1 mole of SiO2 equal to 1 mole of silicon carbide, right? That's why how much mole? So 1664 mole of silicon carbide. We don't know which is the excess reactant and which is the limiting. Now let's find out how much mole of carbon also used. Okay, so that's why yeah, see that. So now this is the SiO2 mole. Now you convert that SiO2 mole, okay, this is the mole of SiO2, and this is the mole of silicon carbide. Okay, now let's convert that silicon carbide into the gram, right? So 1664 mole times silicon carbide molecular mass is how much? Let's see, 40.9. okay, 40.9 gram per mole. Okay, so that is equals to 40.9 times 1664 gram, and convert that into the kilogram, because kilogram is recovered, right? So 40.9 times 1664 divided by 1000, right? Because you divide by 1000 to convert into kg, gram to kg. That is equals to about 66.71 kg. Look at that. So how much recovered? How much you produced? 60.71. This is the theoretical, right? Theoretically, you should have this much production, because 1 mole of silicon dioxide should be 1 mole of silicon carbide. This means your silicon carbide is this many moles. That's why this much kg. So theoretically, and the carbon is excess here, okay guys, because nothing is said about the carbon, which is excess. So carbon is excess amount. When this is used, carbon is excess, unlimited carbon is there. That's why this is excess, and this is limiting. When this reaction is done in the industry, a lot of carbon is used. This is excess, this is limiting. So theoretically, what is theoretically? You should have 66.71 kg. But experimentally means actual, you have 51.4 kg. So that's why percentage yield is equals to 51.4 divided by 66.71 times 100. That is equals to 77%. That is your percentage yield, right? So this way you can find the percentage yield. Okay, now this is the percentage yield. Okay guys, okay, now let's go to the next one, okay, where we will study again the percentage yield example. You see, this is the table. Okay, so now, and so that's fine. Okay, now we up to here the percentage yield. So now in the next topic we will go to the next topic, which is the concentration of the solution and the molarity. Okay, now here we finished up to percentage yield. Okay guys, now we have calculated the stoichiometric coefficients, we compare them, and then we found the limiting reactant, and finding the limiting reactant we found the theoretical yield, and after finding the theoretical yield we calculate the percentage yield. Okay, so this is up to the percentage yield. Now in the next topic we will go to the concentration.